So, Bob, I was, coming from a rural background myself in the South. I was wondering if you'd say a little bit about your background growing up and when you first became aware of math and science and got interested in academic things.
I wasn't quite from as rural a background as you were. I went through sixth grade in Lakewood, Ohio, which was it is a suburb of Cleveland. And then I lived in Oak Ridge, which is fairly rural, I guess. But my father was a physicist, so I was always aware of science. Uh, what's a more interesting story is my relation to mathematics, because my father really didn't like mathematics. As with some other physicists, if my father wanted to really put somebody down and say they had no intuition and weren't interested in the problems of the real world, he'd say he's a mathematician.
Mhm. Were there mathematicians that he worked with there at Oak Ridge? Or?
No, not that he worked with. Later on, when I was in college, I spent a couple of summers there working with Bob Covey, who was a mathematician. There was a very fine mathematician in Oak Ridge, Alston Householder. He was there at the time, but I didn't know him, and my father didn't know him.
But did you recognize it was mathematics when you got interested in academic things, or was it, or were there other things that led that way eventually?
I would say I was mostly interested in science. Um, and in music. I didn't really make a decision to go into mathematics until my senior year of college, where I had to apply to graduate school in something. And until then, it could have been mathematics or physics or music, I guess. So there wasn't really serious mathematics in Oak Ridge. There were teachers. Some of them were very friendly. But the first time I met serious mathematics was in one of the National Science Foundation summer programs. I went to two of those. The first was at the University of Tennessee. That was in physics and chemistry. And the second was at Michigan State University, and that included mathematics. And at that one, I ran into this guy named Fritz Herzog, who was he was the first real mathematician I ever knew. And I was just enthralled with him and his life and his way of thinking and so on.
Did he talk about mathematics particularly, or was it other things in his life that you also found interesting? So.
Well, I mean, he taught us a math course, but it wasn't actually so much the contents of the course. The contents of the course was sort of definitions of groups and first theorems. I don't think people knew then as well as they know now what sort of curricula can appeal to people at that level. It was before the Ross program and so on. Well, there were some other people in the class who thought they were interested in science. That's why they went to the thing, but I remember one of them explaining that he had decided as a result of this summer that he didn't want to do science. He didn't want to do mathematics. And so Herzog asked him why not, and he said, well, it doesn't involve people. Herzog said, well, you can get tired of people. I don't get tired of my numbers. And I remember being really turned on by that statement, the fact that he loved it so much.
Go back a little bit in high school. Do you feel that you got encouragement in science and math in high school, or they didn't know what to do with you?
Yes, they realized that I was unusual, and they tried to encourage me, but nobody really knew what to do. Um, so my father, for example, he bought their Dover reprinted some of these old problem books of Dewdney. You know, this guy who in the 1800s wrote puzzles for the London newspapers. And well, I mean, these were interesting. They were inspiring in some sense, but they never really got to the mathematical essence of something. I mean, often the solution to one of the puzzles meant sort of interpreting a word in a different way or something like that. I mean, they were more sort of mind teasers than real mathematical puzzles. I did spend some time with those. And some of my teachers suggested that I read other geometry books, but I was never given a book by a real mathematician. At that time, I don't think anybody in Oak Ridge really knew what to do, knew what good books would be.
Mm-hmm. Right. So they didn't hand you a calculus book or anything like that?
No, somehow the feeling at that time was if you learn, I was the last year that didn't take calculus until college. The general theory at that time was if you learn something too early, it will be bad for your development because then you'll be bored when you learn it later on, which seems to me a terrible theory, but that was the going educational theory and also what my parents believed.
So things were too structured in a way to really appeal to somebody who was like you, who was probably interested in a lot of different things at once. And
yes, one of the wonderful things they did at Michigan State, for example, was they had, I guess what now you'd call a Putnam problem-solving session. People who were interested would just get together and solve problems together, and that was an incredible positive thing for me. So I came back to Oak Ridge High School, and I thought, oh well, let's organize one here. Why can't we? And well, there just wasn't the interest. You know, persuading people that they ought to stay after school to solve mathematical problems. That seemed like a very funny thing to do. And then later, of course, when I went to Moscow, I realized that that was exactly the secret to Russian mathematics. All of the Russian mathematicians we know were involved in groups of the type that I was trying to organize in Oak Ridge.
do you keep up with or know about what happened to your colleagues in those summer programs at all?
The colleague who impressed me most was a guy named Steve Crick, and then we ended up in graduate school together. It was a very sad story. He had some sort of mental illness, and it degenerated, and I think it ended up taking his life some years later. Even at the time, I sort of realized he was in trouble, so I asked him, to come and share our apartment with us, because I thought he needed somebody to look over him. But he was very talented, and he was an inspiration to me in high school. Other countries do a much better job than we do getting people who should become mathematicians, who grow up in some area where there isn't so much strength, and getting them into mathematics. I mean, the United States is very good at it. If you grow up in northern New Jersey, for example, you'll get all sorts of recognition. You'll be taking college courses sometime in high school, but not if you grow up in Tennessee. Whereas in China, somehow, if they find mathematical talent, they manage to find those people and bring them together. Well, the United States did that after Sputnik, when they introduced all of these summer science programs in the high schools. There were, I don't know, between 50 and 100 of them. I mean, there were lots, and those played that role. But then at a certain moment, that program got canceled, and I think we've lost a number of potential American mathematicians because of that.
Math circles structure growing in this country now,
right,
in lots of different places. Do you see that as some kind of way of trying to recreate some of that excitement that you saw in the Russian?
Oh, it is definitely.
Programs?
I mean, it's done by those people trying to do it. What we lack in this country compared to Russia, in Russia, virtually all good mathematicians that were not earning their money doing mathematics. They had some other job where they'd get their money, and they did mathematics for the love of it. And so long as you're doing that, you might as well run a math circle for all of the kids of you and your friends for the love of it. We don't have that spirit here. I mean, the idea that the very best mathematicians in the country would be running math circles for high school kids. the people who do it, the ones I know who do it here are people who were sort of educational experts in Russia rather than research mathematicians. But yes, it's certainly an attempt to recreate that.
You mentioned music a little earlier on. So at that time, in high school and college, you were pretty intensively studying music as well as getting turned on to mathematics.
Yes, that's right. I actually, in terms of coursework, I spent an equal amount of time on mathematics and music and physics in college, but because the mathematics was so easy for me, in terms of hours, I spent much more time on music. Yes, it was a very serious interest, and I still think music theory, well, I mean, I was considering becoming a composer, a music theorist or something like that. And
could you say what appealed to you about the structure of composing compared to what appealed to you about solving problems in math, or do you think they're really different, or
I think they're
or
really
related?
different. So, of course, as everybody knows, they tend to operate in the same people, and now that people are doing brain scans, well, people actually think for the first time, I expect that some common overlaps in the brain will be found. But I can tell you what my experience, when I was taking counterpoint, this was from Schoenberg's counterpoint book. The counterpoint exercises are, in a sense, puzzles. The same exercises have been going on for about 500 years. It's a very, very developed thing, sort of like doing integrals in mathematics. I mean, so the exercise typically gives you a cantus firmus and then the first notes, and then you have to fill in the other voices with certain rhythmic patterns, and you have to avoid certain bad sounding combinations and emphasize certain good ones. Well, you can phrase this as an exercise in combinatorics. Can you just solve this problem? And so I tried solving it as an exercise in combinatorics, and I discovered it was so incredibly hard I couldn't even get off the ground. It's just way, way too hard to solve mathematically. On the other hand, if I just listened to it and with my inner ear thought about it musically, I would just write out the answer. The answer would just come. So I concluded from that I don't believe the formal explanations people give. I mean, everybody loves that the Fibonacci numbers occur in the fugue entries in Bach fugues and so on. I mean, yes, Bach loved things like that, but that's not why Bach is great. And
I mean, you made the analogy with integrals. It's sort of the fundamental things that have to become so natural that you don't even think about them.
Right.
That you start working at a higher level.
Right.
And
Right.
But there is a higher level, and you
Right.
and you break through to it after you get the fundamentals to some sort of automatic state somehow. Right.
Right, and Bach enjoyed the challenge of breaking through to the higher levels while posing himself a whole bunch of arbitrary constraints. He was such a master that he could do it, but that doesn't mean the arbitrary constraints had to do with his composition method.
Right. Yeah. So were you particularly attracted to that kind of very high polyphony and counterpoint?
Well, I love
Bach,
counterpoint,
say?
yes, but
Yeah.
I mean, I don't think particularly that aspect of it, but yes, yes, definitely.
So you said at one point that you kind of had to make a choice about whether or not you wanted to continue in music or go on into mathematics. Can you recreate any of what was going through your mind at the time that you were making such a choice?
Yes, I can actually, because the final deciding factor was very definite, and I don't. Okay, so the factor was this: at Swarthmore College, the music department consisted of two people. One was a musicologist and one was a composer theorist. These two people couldn't be civil to each other. They couldn't even be civil about each other. Even when talking to a third person, they couldn't say anything nice about each other. Whereas in the math department at Swarthmore College, everybody was quite friendly. And so I decided I didn't want to be in a subject where there were these personality conflicts. And I think I was right. As near as I can tell, it's still the case that if you're, well, I mean, maybe less now than it was for the couple of decades after. I mean, the first decades I would have been in music if I had gone that way. But it was the case that if you were a composer and you composed tonal music and somebody else composed 12-tone music, you wouldn't respect each other, or there would be wars between musicologists who would study medieval music and musicologists who would study African music or something like this. And it's still true, really, that musicians, I mean, they have friends, but they have enemies as well. I just don't see this in mathematics. You know, some people do analysis, some people do geometry. They respect each other enormously. Everybody knows that what they're doing is so hard that if you are able to do it at all, it's an amazing achievement and you deserve some sort of respect. So I think the reason that I chose actually turned out to be a correct perception, even though, you know, even though my sample was very small, the law I drew from it was true.
When you did decide to start studying mathematics more or less exclusively for a while, when you in your training period, what were the things that attracted you the most at that time? I mean, your interests have varied so much over the years and gone in so many different directions. I'm just curious how things looked when they got started.
Well, first of all, I have to say my time in graduate school was probably the most unhappy time of my life. For a number of reasons. But nevertheless, I did fall in love with certain areas in mathematics. Actually, by that time I had already written my first mathematical paper, which was in college, and so that's a separate story. But well, I fell in love with geometry. Grassmann manifolds were just the coolest thing I'd ever seen in my life. And then when I realized that they had subvarieties which were singular and that you really cared about them and their singularities, I mean, this turned me on in an enormous way. And well, I've never gotten over that.
Yeah, that's right. Yeah, who knew that Schubert cells could be so beautiful? Right. Schubert
Right.
cycles.
Right. Right. As soon as I saw the definitions, they just, it's like they went directly to my soul in some sense. There were a number of things wrong with Harvard at that time, which have I mean, when they moved to their new building where everybody could be together, and also there was some change of personnel, they got over many of these things, but it was there was a lot of competition. There was a lot of orientation towards exams. The qualifying exams were very cruel, actually. So all that aspect of it, I was very upset with.
But were you talking more with the algebraic geometers there, or I mean, who were you kind of following at that point when you were at Harvard?
I was
as a graduate student.
I was not really talking mathematics with anyone. Of course, I was in a culture that that respected mathematics, and that was important. With my own graduate students, I'm always, I talk to them, and I book long periods of time with them. I mean, if I can't have a 3-hour block, I mean, I want to talk to them, and I want to sort of get into their own language and learn how they think and use words the way they use them, and so on. And I don't recall anyone at Harvard doing that with their graduate students while I was there. So I completely idolized Raoul Bott, and I read his papers. But we maybe had, I don't know, 3 or 4 mathematical conversations in the 4 years I was at Harvard.
But Bott was a very welcoming figure in a way.
Absolutely. He was a wonderful guy. I loved him personally.
Uh-huh.
Yeah, and as I said, I completely idolized him, and I read his papers on Morse theory, on Lie groups, were just a complete inspiration to me then as they are now. I think it's one of the great things in mathematics. I actually learned that stuff when I wasn't even at Harvard. I was visiting the University of British Columbia for the summer, so I studied all that. He never talked about that while I was there. He was doing other things. I went to every course he taught, but it was all about Lefschetz fixed point theorems for elliptic differential systems and so on.
Mm-hmm. Right. Yeah. Because he'd done the work on periodicity and so forth back in the 50s, I guess.
Right.
And so, yeah.
Right. It was very moving. Then a few months before he died, he knew he had lung cancer. We all knew he was going to die, but I asked him if he wanted to come to the Institute for Advanced Study. We were holding our 75th anniversary, and I was in charge of the mathematical part of it. So he said yes, he definitely wanted to. He had done almost nothing mathematically for a long time at that time. So he came, and at that time he did give a talk on that work, because that's the work he had done at the Institute for Advanced Study 50 years earlier. And so that's the only time I heard him talk about it. His hand was so unsteady at that time that he asked me to prepare the blackboard for him. So I drew the roots and weight lattice of A2, which was his favorite example. His hand shook too much to do it, but once it was there, he could show the ideas on it. So at that time, just walking the 100 yards from the housing project to the math building, he felt like he had climbed Mount Everest. It was just a huge strain for him. The very cycles that he introduced in the proof of the periodicity theorem, I had been studying, and many other people. I mean, it had come into algebraic groups, but we were studying them now as algebraic varieties. He was studying their homotopy class, and we were studying them as varieties and looking at their singularities and taking their intersection homology and so on. So I mentioned this to him, and he said it would be his dream to come back to the Institute for Advanced Study and have another semester of work like he had in the 50s.
Yeah, I didn't see him in his last few years, but I remember him as the big bear.
He was still the big bear.
Yeah.
He may have been weak, he may have been shaking, but his personality was always bigger than life. Actually, I have a very funny story about that. I mean, because in general, Harvard had a lot of verbally aggressive types, and he interacted with them just beautifully. He would love to parry with them, but he understood that I was a different sort. I was sort of shy, and so our personal interactions, which were always very warm, were of a different nature. So I remember walking with him to his class, and he was walking slowly, and he commented, "I'm so tired." This was actually a politically interesting time. Martin Luther King had been assassinated recently, and everybody was upset, but things were going on. But this was a room in Barson Holly that had a sort of a room that off of it that the teacher could go into and sort of prepare to come out. So he went into that room walking very slowly. I'm so tired. And then he came out 2 minutes later, tall. "Well, kids, how have you been doing on my..." I mean, huge, big gestures of the Raoul Bott personality. He could just turn it on and turn it off. Yeah. He was a great actor, and it was part of his personality. I'm not saying it was false. Right. It was really part of it.
He was very much an extrovert in the sense that being around other people gave him a huge amount of energy.
Right. Exactly.
And he played it very, very wonderfully.
Right.
One of a graduate student at Harvard once told me a story about hearing Bott give this amazing lecture on characteristic classes there, and at the end of the lecture, the students came up to talk with him, and wanted to see what his notes were, because he'd come in with a one-sheet page and put it down and basically never looked at it during the entire time that he was lecturing. And they looked at the note, and there was a big theta written on the sheet, and that was it.
I know, right? Theta for him was always a differential form or a matrix of differential forms, and that's all he needed.
Right.
Well, every course I took from him always was the same pattern. He would start and he would get to a certain point and it would seem very slow. And then he'd come the next time, he'd start at the beginning again and go faster and get twice as far. And then he'd start at the beginning again, go much faster, get 3 times as far. It's a great way to teach.
Yeah, he wanted to make sure you understood the fundamentals.
Right,
Yeah,
right. I mean, it really worked when he did it. I don't know if I could do it, but
yeah, that's right. It takes a certain personality to be able to do that. That's right. Yeah. Yeah, it must have been really fun. I did meet him a few times, and of course I read those papers too, because I was, like you say, they're classics. Were there other people at Harvard that you talked with?
there were a few graduate students I was friendly with, but in general, we didn't discuss mathematics so much. So I got started on singularities at Harvard. As I say, Raoul Bott and I had only a few conversations, but one of the very early conversations, he suggested that I read a paper of René Thom that he wrote in the 50s about characteristic classes and singularities of the maps and so on. This paper, well, I wish mathematicians were bolder about writing such papers. It was full of half-baked ideas, half-proved theorems, definitions which weren't quite complete, just lots of interesting stuff. And nobody, well, Raoul said that nobody had followed it up, and he thought there was probably some good stuff in there, and he suggested that I look at it, and I did, and it turned me on to singularities of maps, singularities of spaces, and in some sense, everything followed from that. So as I say, we didn't have many conversations, and the essential part of this one lasted maybe 30 seconds, just to go read this paper, but it was worth all the money in the world, anything you could say. Right, so I got very turned on to singular spaces as soon as I knew what they were, and as we discussed earlier, I then met them in Schubert varieties and Grassmannians, met real live examples that were very interesting. And I sort of came up already at this time with my philosophy. At that time, everybody in algebraic geometry, everybody in differential geometry, they would all assume their space was non-singular from the beginning. So I thought, why is everybody studying manifolds? And well, you know, there are these justifications. We're interested in manifolds because, I don't know, Hamiltonian mechanics takes place on a manifold. It doesn't. It takes place on a level surface of a Hamiltonian. There's no reason that has to be a manifold. Anyhow, in every case, every argument, or one of Poincaré's original arguments that we're interested in manifolds because of Lie groups. Well, as soon as you look hard at a Lie group, singular spaces are all over the place. So I was going around already as a graduate student making this case that every argument I'd ever heard anyone make for studying manifolds was really an argument for studying singular spaces, and yet nobody was doing it. Why not?
And by singular spaces, you mean something far more serious than just V-manifolds or orbifolds.
Right.
We talked a little earlier about how we make these gestures to, indicate smoothness, and you did that with your hands. And do you have a gesture that you characteristically do for singularities?
No, it's a little hard. I remember my second year of graduate school already dreaming about singularities, and they're sharp things. If you touch them, you'll cut your finger. So it's sort of hard. Any gesture with your hands falls short of the
Yeah, right.
of the magnificent
Can't touch
essence
it itself. Right. Yeah, right.
of a singular space. Actually, I have another funny story about Raoul Bott. Although he got me started on singular spaces, he never really bought into it at that time. So when I came up with my thesis result, my first proof of it involved a certain construction. I would start with a manifold and start doing various identifications and end up with something, and I started describing to him. And he said, "But that's an ugly space." And I said, "It's not, it's a beautiful space." And he said, "It's not even a manifold." I said, "It's a stratified space." So he wasn't convinced at that time. I mean, later on, he was very convinced. When the theory was more developed, he certainly became a partisan of the theory. But, so he insisted that I go out and find a different proof that didn't involve introducing this space which he regarded as ugly. And I did. I spent a year doing it, but I found another proof.
Did you feel that you were just basically translating the insights that you had from the singular space construction into something artificial but still more conventional?
No,
so
I didn't. I
so
thought
it
I
was useful to think about, of the alternative way.
It was enormously useful. Of course, he was right. There was a it was a theorem about characteristic classes, and certainly Raoul Bott's going to be right about characteristic classes. So, I mean, it involved reducing to a universal case and then constructing various auxiliary cases, as was the style in those days, and it was highly computational. But in the end, my original construction reemerged. When we studied, when I introduced Chern classes of singular spaces, and then Paul Baum and Bill Fulton and I introduced Todd classes of singular spaces, and in both of these, to prove results about it, we basically had to reduplicate my original construction, but in the realm of algebraic geometry. And since it was an algebraic variety, people wouldn't complain so much as Raoul.
Yeah, that's right. Yeah, that's right.
It was sort of
Everybody
okay.
knows you got to live with singularities in the algebraic case, right?
Right.
Did Chern have any reaction to your extension of Chern classes to the singular spaces this way?
I never discussed it with him. I mean, he must have had a positive reaction. Chern tried to get me to come to Berkeley, and I must say he was the most magnetic man I've ever talked to. I mean, it was as if I was hypnotized for about a month. There was nothing I wanted more than to come to Berkeley. Mark wasn't so enthusiastic, and in the end we didn't do it, but no, he didn't. We didn't actually discuss that.
But you did spend some time in Berkeley. You visited Berkeley from time to time.
Oh, yeah. Yes, absolutely. When the NSF put out a call for forming another math institute, there were a lot of powerful people who wanted it to be in Boston or someplace else on the East Coast, and I felt that would have been a total disaster. It's just wonderful that it's in Berkeley. We all get a chance to go to Paradise occasional.
I'm glad to hear you feel that way. You're always welcome there. So you mentioned Mark. When did you guys start collaborating?
So I went to Brown in 1970. It was my first job. I went as a postdoc, a Tamarkin postdoc. They still have Tamarkin. Instructors, they were called at the time. And I sort of stayed on. Mark came as a graduate student the next year. I think it was Bill Fulton he was taking a course from Bill Fulton. I think it was Bill Fulton who suggested that he come and talk to me. And so he ended up being my student, and I recognized he was a very, very exceptional person. So I actually proposed to him a thesis involving singular spaces. So and he was already working on this. And then at a certain moment, I decided that it would be a good thing to go to the IHES because so many of my mathematical heroes were there, and I had never done it. So I was set to spend a year at the IHES, and they arranged for Mark to come, and even though he was, I don't know, a third-year graduate student maybe, they were happy to host him just like they would anyone else, and it worked out very well. It was actually while we were there that we discovered intersection homology theory. We were doing it as a sort of a side joint project to his thesis work.
To get back to intersection homology and the construction of this beautiful geometry and singularities that you were working on at that time, what would you say were the things that were feeding into that you thought of as what would be, I don't know, applications or ways of reaching out to other areas in mathematics that intersection homology would do?
Well, as I already said, I felt that any argument that manifolds are interesting was really an argument that singular spaces were interesting. I think that's been vindicated in years past. This has been, after the tools were there, this was put in place. Well, some mathematicians in the 50s already were trying to study singular spaces, but they also were trying to do it without grounding in singular spaces that come up in nature. I mean, they thought, okay, well, how do I make a singular space? Well, maybe I glue various sheets of manifolds together and form a singularity. Well, okay, yeah, that's one way, but that's not very interesting. The world's beautiful singular spaces tend to be algebraic varieties, and so you should start with those. Well, fortunately, Whitney and then Tom were laying foundations, and John Mather was involved. He was doing his work in this while I was at Harvard, and he was there too, and that was a great boon. So.
Oh, you talked much with John Mather when he was doing the stability?
Well, again, I was personal friends, and I went to all of his lectures, so I got lots of inspiration. We had the advantage that we were able to look at the right class of singular spaces to include the examples that one wanted to apply it to. Well, we actually set about to understand homology. At that time, people said, well, there's homology and there's cohomology, and they're totally unrelated. Cohomology has a ring structure. Homology is weaker because it doesn't have a ring structure. That was the sort of catechism. The thesis problem that I suggested to Mark was a way to view cohomology and a way to view homology that saw them as quite parallel, but with different restrictions on how they intersected the singular set. Well, it was completely apparent to us that these were only two of the possibilities, and that maybe one should explore other restrictions. We didn't know it would work out as spectacularly as it did. We were imagining that there would be some theory that you would take a couple of cycles. I mean, we had lots of examples where you would take a couple of cycles and their intersection would be defined, but maybe not completely defined. Maybe it would be modulo something that came from the singular set, and only certain cycles could be intersected. So we were expecting some theory like that, and we're quite. I mean, as soon as we got what we did, we immediately thought that this has got to be incredibly important. In fact, Mark tells me the day we sort of verified that we had these many groups, and one of them satisfied Poincare duality. I apparently told him, this is the kind of thing you'll find once in a lifetime. And it's true.
Were you talking with Tom then, or was he around? Or
Well, he was one of my heroes, and I spent a total of 4 years there. And I always went to every lecture he gave, including his lectures on social sciences or humanities or whatever. But talking, not so much. I mean, sort of like Raoul Bott. We were personal friends, and I talked to him about non-mathematical things, and I studied everything he wrote. But no, we didn't actually discuss mathematics so much. Actually, at his 60th birthday party, I was discussing a certain construction, and I pointed out that you could regard the construction I was discussing as catastrophe theory on a space that itself singular. So you had a smooth function on a singular space and looking at the catastrophe theory. And afterwards he came up and he said, "This is very interesting, but you know, I have some advice for you." He said, "I wouldn't use the word catastrophe theory." He said, "Catastrophe theory is so poorly thought of now that people won't take you seriously if you say you're doing catastrophe theory."
so he was aware of what the outside world sort of was.
Well, you're right. I mean, this was after the backlash had been sort of there for some. The backlash, sort of, I would say, in response to maybe Chris Siemens overselling the ideas.
So do you think there was that, you know, that sort of brand of singularity of maps and things like that got too closely associated with the study of singular spaces, the kinds of things you guys were doing?
So there was a whole subject that dated from the time that catastrophe theory was in vogue of singularities. I mean, to the extent that people thought maybe they should have their own journal, and people would go to conferences together, and I went to conferences with these people. I mean, they recognized what I was doing was part of this. Now I believe that mathematics is a unified whole, and people shouldn't sort themselves off in sub-disciplines like this. And the people doing singularity theory, even though some of them were differential people who were doing Whitney stratifications, other people, or singularities of smooth maps, and other people were algebraic geometers, even though they spanned that gap, they were still a very ingrown group. So I remember a talk I gave in one of their seminars in the very early 1980s, advertising that singularity theories people should be interested in modular forms, because if you take a modular variety and you compactify it, it has singularities that are so much more interesting than anything these guys were studying. And so I just explained to them how you could think about this in a more elementary way, because admittedly the people who do modular forms have their own in-group, and they talk about Adels and so on, and if you don't know that language, they say, okay, well, you don't deserve to know what I'm doing. So I explained to them how they could think about these modular varieties without understanding the language.
Geometrically.
And nobody took it up.
Huh.
And then the singularity theory sort of died a death from ingrownness, I would say. And I sort of feel I was offering the cure at the time that it
At the time that it would have done.
And they didn't do it, but I went off and was doing modular forms for almost 2 decades. And I think what killed singularity theory was definitely not the backlash from catastrophe theory, because everybody recognized that what they were doing was proving theorems. I mean that it was a completely separate thing. It was rather that they weren't willing to get an infusion of new ideas from other subjects when they needed one.
How did you come up with the terminology of perverse sheaves? maybe I'm falsely attributing that to you.
No,
but,
no,
yeah.
no. In fact, intersection homology was to be called perverse homology. That's what we called it. And Dennis Sullivan told us you can't do that. And so then instead Pierre named something else, something close related, perverse. The idea was sort of the cycles that spend all their whole life in the non-singular part, well, they can intersect with anything. But some cycles sort of perversely go straight into the singularity and actually can't be pulled away from there. I mean, so it's not that they happen to wander in by accident. They're going there, and that they're attracted to it, and that seemed to be perverse behavior to us, and it was perverse in the sense that it made it hard for that cycle to intersect. And so our perversity is the number we associate in our paper. The perversity is a measure as to how much the cycle is having this perverse behavior. Of course, at the time, we were thinking of the English and the French meaning of the word, which are sort of humorous and ambiguous. It turns out, I guess, maybe the German and perhaps the Russian meanings are quite a bit more negative. We didn't know that.
It's interesting that you would describe it as perverse, that they would want to go to the singularity, since you wanted to understand things by going to the singularities. Pretty much, you thought, and we're right, that this was the key to understanding things.
Definitely using it in a humorous sense. I mean,
right. Ironic sense, I guess.
Right. You know, a kid who perversely insists on something, well, maybe that kid is Gauss. And
So that must have been a very exciting time. I mean, can you say more about what was kind of going through your heads? I mean, once you realized you had a tool like that, you must have thought, oh, I can do all kinds of things with it. So.
Well, so we actually found it in 1974, and kind of in the fall of 1974, and kind of sat on it for a while. So the first problem was this was joint work by agreement, but Mark had to write a thesis, and so we came back and sort of put it on cold storage. Nobody else was anywhere close, so it didn't much matter. Then, I remember, I think the only people who really liked it the first time they heard it were George Lustig. I talked about it at Warwick when he was still a professor there, and René Thom when I talked about it in Paris, and also Pierre Deligny when I talked about it in Paris. So all three of them immediately said, there's something new in the world, this has got to be absorbed. But most people's response was, okay, these guys are defining another homology theory. The last thing in the world this world needs is another homology theory. We already have the one that has the right properties. You know, it's very cute. When we submitted our paper, they asked us to cut out some of it because they didn't want to take up that much journal space because it was very cute. Later on, of course, we had to republish that part somewhere else because people were, asking for it. Right? We did a simplicial version of intersection homology, and people were saying, well, what's the simplicial version? So we had to sort of insert it as an appendix to another paper.
Just because you recognized how important it was doesn't mean that everybody else recognized it at the same time.
Everybody thought that manifolds were it. And, of course, for manifolds, if they're oriented, cohomology is homology. You have everything. What more could you want?
So it took a little while for people to realize how important that was, but gradually people did catch on. There was, I mean, your work has certainly been recognized in many different ways, prizes and conferences and lots of people following the work and making use of it.
Right. Of course. Well, when it finally started having applications, then I mean, one group of mathematicians or after another had to adopt. I mean, one of the most painful was the finite group theorists. When George Lustig started using it to construct interesting representations of their favorite objects or interesting ways of understanding, then they were really quite resentful because they felt that they shouldn't have to learn any topology whatsoever. And here suddenly they had to finally learn this rather funny kind of topology. And the same happened with the people in modular forms and the people in algebraic groups and so on, algebraic geometry. But the theory was sort of around. I mean, we didn't even publish it until 1977. That was the first announcement, and then our longer paper was after that. Part of it was as I say, we had to officially put it on cold storage until Mark got his degree, and then there were various personal things going on and so on. So it took a while for the paper to actually get out.
And during that time, you were doing other things as well, it seems.
Yes. Of course, when I was in Paris at that time, the popular thing I had done was the singular Riemann-Roch theorem. Verdier and Doady were running their École Normale seminar about that year. So that was what. It was very funny because all the this was the descendant of the Cartat seminar. I mean, Paris always had this one sort of central seminar. So it was what all the young people were talking about of the year, and it was my work, and yet it wasn't what I was excited about. I was excited about this other thing. So, I mean, for me, it was the thing I had done the year before. I remember Doady was very excited about the graph construction, which, by the way, is a special case of this thing that Raoul Bott had told me was ugly. And so the first time I met him, he was very excited. He started explaining it to me. He said, here's how you can think about it. He said, but wait a minute, aren't you one of the people who discovered this? And I said, yes. And he said, okay.
Yeah, that's a bit awkward.
Well, Doady was something else.
Yeah.
He was lovable no matter what. He was such a fantastic person.
Of course, a legendary guy. So.
Right. Right. We always love our eccentrics, mathematicians.
You had just said we love our eccentrics because we'd been talking about a few, and I said, and I pointed out that that's very different from what people imagine mathematicians are like, which is that we're kind of bound by our definitions, maybe a little dry, working logically all the time rather than by inspiration.
Yes, many people get confused in their mind between mathematicians and accountants. They think what we do is multiply very large numbers or something like that. And not that I have reason to believe accountants are dry. Well, I like very much Kolmogorov's view of how someone can be a scientist. This view is not known so well in the United States, and not actually even known so well among most Russians. But he was very serious about it. So he said, all organisms, he was an expert in child development. He said all organisms, not only people, are very playful when they're young, and are more serious when they're older. Well, this is they have to be. When they're young, they're exploring their world. But when they're older, they have to bring up their kids, and so they need a more stable world. So curiosity goes with the playful stage. And he said, now scientists have to somehow maintain their curiosity throughout their whole life. And he felt that this was going against the way humans, and in fact chimpanzees and essentially all mammals are conditioned for. So his feeling was that the only way somebody can be a scientist is if somehow their personality gets frozen at an early age, frozen at the playful stage. So he had one of the games that he and his that he and Alexandrov would play a lot is talk about the ages different people had. I mean, his theory was that every scientist, every mathematician has a certain age, somewhere between 4 years old, say, and some 18 maybe, some teenager. They have to have been frozen at some point along this. On the other hand, different people are frozen at different ages, and so therefore you could see different people's personalities by the ages they were frozen at. I learned this theory, by the way, from Gelfand, who learned it from Kolmogorov, and Gelfand himself believed in it strongly, and we discussed it many times, and he would tell his guess of various people's ages. So Gelfand thought that my age is approximately 8. I think he's probably right. We were just talking to Jim Simons. Every time I meet Jim Simons, I feel like I'm the kid and he's the older protective teenager. Whereas whenever I'm talking with, for example, Pierre Deligne, I feel like I'm the 8-year-old and he's like the kindergartner. You just sort of feel this. I don't know if it's true or not, but I believe in it, and definitely Douady was a little kid. I mean, some people think that he went around barefoot and long hair and all this in order to be outrageous. That's just not the case. I mean, he did it. He was having fun. He was having fun with life. I don't know. I'm not a child development specialist myself, but I think he was frozen at a fairly young age. I think, yes, mathematicians have to be playful. If you're not playful, you just can't do creative mathematics. There are some non-playful applied mathematicians who write, I mean, I'm doing applied mathematics now. I've met some of these people who write computer programs. But I think that at the highest level, all scientists have been frozen at some early age.
At what point did you become involved with the Russian mathematics community?
One thing I have in common with Jim Simons is we were both obsessed with finding a combinatorial formula for Pontryagin classes. This is, I mean, to me, it's an example of a singular space. You have this combinatorial manifold with flat edges and the curvature is concentrated someplace. You ought to be able to find any curvature measure associated to it, and of course, for many of them, you can. But for Pontryagin classes, well, that's sort of harder to do it in an explicit way. Everybody feels. The whole list of very fine mathematicians have all felt that there should be a very simple natural answer, but no one has ever found a simple natural answer. In any case, Gelfand along with Gabriela von Losek found an answer for the first Pontryagin class of a 4-manifold, and I got fascinated by that, and I worked out my own version of it, my own proof of it, and then I met Gelfand and sort of completely became enamored of his personality. He visited Paris then later in, I think it was approximately 77, maybe the spring of 77, and yeah, the spring of 77. It was his second time that he was able to go to the West. And he sort of, his way was always to sort of glom onto some younger person who would sort of be responsible for keeping him organized. So I would carry his pack and keep him from losing things and making sure he was no more than an hour late for his appointments and things like that. And during that time we talked all the time. And so he said at that time it would be wonderful if I came to Moscow. And later on I discussed this with Yasha Sinai, who was also visiting for a short time. There were very few Russians who could go out, and very few occasions they could go to, but anyhow, Sinai managed to do it, and Sinai told me he thought I would find it very interesting. So I decided to to try it, and I went there for a half a year. It was a sort of a dramatic thing because I was scheduled to go in January of 1980. Well, Russia just invaded Afghanistan, and I was going on an exchange program, and Jimmy Carter, president, was on the air all the time saying in punishment for Russia's transgression, he was canceling all exchange programs with Russia. And so then I would call those people, is it canceled or not? And they say, we don't know. So I had to make some decision, get on the plane or not, and I decided get on the plane. And so then at that point, I met a whole range of Russian friends that I'm close to. And until today, very few people went to Moscow at that time. Very few mathematicians, and so. Right, I worked with Gelfand, but also with many other people. And then I went back essentially every year until the collapse of the Soviet Union, at which time most of my friends who were the good mathematicians all got jobs in the West, and so they all left. And so if I wanted to see my friends, that's the one place I couldn't find them anymore. So at that time I became involved in I guess it was my idea to create the former Soviet Union Aid Fund. And we helped a number of Russian mathematicians over at a very difficult time. After communism collapsed, their salaries stopped, but they hadn't found any other accommodation, and so they were having a hard time making ends meet. On the other hand, it coincided with a period of time when the exchange rate between the ruble and the dollar was such that you could support a family of four comfortably on $50 a month, so that's what we paid them. And anyhow, many people made the transition, basically supported by this American money coming in.
And how long did that go on?
That went on for 2 years. We had funding for 2 years, and that was just about the period of time that we had this favorable exchange rate. So to extend it, we would have had to have a source of far more funding than we did, and besides which, ultimately, people have to reach accommodations, and Russian mathematicians did reach their own complicated accommodations. For example, some people spend half a year in Moscow and then spend half a year in Kyoto. And there are many complicated arrangements. Or some people have a teaching job on the side. I mean, there are many ways people make ends meet.
You said a lot of your friends actually came out to the West in one form or another, but you still maintained contact with people in Russia, I guess. I mean, during the supporting people who were there.
Yes, yes. Some people have not come out. So one of the things we did is with this aid and also with the Western prestige is create the Independent University of Moscow, and it was created just before the collapse in about 1990 or 91. They're going to hold next year their 20th anniversary conference. I went back for their 10th anniversary conference. This is enormously important. Some people feel it's not important anymore. So you have to understand the huge paradox of Russia. During the 80s, the Brezhnev era, the official mathematical organizations like Moscow State University and the Steklov Institute were totally corrupt. In fact, it was better if you wanted to get a job there if you weren't a good mathematician, because the party hacks who had the jobs would feel threatened by a good mathematician. So they actively discriminated against people who were doing excellent mathematics. So on the other hand, there were all these excellent mathematicians who had jobs that didn't require so much of them, basically, in my view, because of the sort of laxness of communism. They could get a paycheck and not produce very much for it. So they were doing mathematics as a hobby. Now the official institutions have become much better. They actually try to hire people who prove good theorems. And so some people feel the independent university is no longer needed. I feel the exact opposite. I feel it's because of the independent university that they shaped up their act. As long as they had a monopoly, they could continue hiring hacks and their friends. But when the independent university had world-class recognized mathematics going on in its seminars run by, I don't know, Arnold, all sorts of people like that, they had to change.
Do you think the culture that had inspired math circles in the U.S. is still there in Russia to be nurtured?
Yes, in fact, this building of the independent university is somewhat like the building we're in. The first floor of it is dedicated to math education, and they do all sorts of national things. Russia. So I don't know if it's true now. I don't know to the extent it's true now. When Gelfand was there, he had this correspondence school. So if they discovered some guy in the analog of Tennessee or North Carolina who had talent, well, he could sign up for Gelfand's correspondence school, and then he would have these beautifully written geometry books, for example, with really neat, hard problems, and they would write out their solutions to the problems, send it to Moscow. It would be read by a real mathematician with real comments going back, and if they showed real talent, they would be able to go to Moscow or perhaps one of the other centers for university. So they were able to get people, find the best people and bring them into mathematics. And it's my impression that the same thing is still going on. I don't know the details as well because, as I say, most of my friends have left. But I do have a number of friends who are still there. They're very good people, and they're doing it. I trust what they're doing, so I think it's probably very good.
When you first went to Moscow and got connected with the mathematics community there, can you tell me something about what your impressions were, what the things were that attracted you the most about the mathematical life there?
Yes, it was a mathematical paradise. I feel very strongly about this. During the decade and a half after that I went there every year, as soon as I arrived in Moscow, I'd start feeling really good. And as soon as I left, I'd feel very sad. Well, as I already explained, the good mathematicians were doing it as a hobby, not because they were paid to do it. So this already changes the general environment. There's no point in trying to beat somebody out to a theorem if you don't get any credit for the theorem anyhow. In the West, if you've proved a good theorem, maybe you get an offer from someplace, maybe your salary goes up. There, it was totally irrelevant. So that's perhaps a cause. There was no offices. There were places people would gather, like the 13th floor of Moscow State University, but no one had a private office. So people would gather over kitchen tables. These kitchen tables in Moscow are the warmest places I've ever seen. So maybe all afternoon you spend doing mathematics over the kitchen table, and then it comes time for dinner, and then this amazing Russian feast, which is sort of hard to describe, but consists of, I don't know, maybe 20 little tiny dishes, each of which is sort of delectable and made somehow from what's available in the market, which is very limited. And then everybody is, all this good feeling is around, and people are drinking vodka and so on. Anyhow, it's a wonderful thing. But this idea of doing mathematics over the kitchen table, it's hard to describe what's so wonderful about it, but it was, every apartment had a good kitchen table, and it was usually the only table in the house you could possibly do mathematics at, so that's where it was always done. Right, and as you know, these people were doing it at the highest possible level. I mean, there was the Gelfand seminar, for example. So this played a very interesting role. The Gelfand seminar formally started at 7, but it never started on time, of course. But people would start gathering around 6. And then all of the people who were famous in mathematics in Moscow from that time would start assembling, Manin and Arnold. They would all just gather and start talking in small groups. A very typical Russian formation is 2 people are discussing mathematics and they slowly walk to the end of the corridor and then they turn around like this and they slowly walk back. So you'd see these various, or else there would be a group at one of the benches. And one of the things that happened during this time is if people decided they needed to talk longer for research purposes, well, they would make the appointment at that time. And then one of them would go to the other's house and they would gather and talk on the kitchen table, as I mentioned. And then Gelfand would start the seminar at around 8, and of course it was a famously characteristic seminar. It was very rare that the speaker could get 2 whole sentences out without an interruption. Or Grinfeld seminar, which was almost the opposite in nature. Anyhow, I just haven't seen anything in the West comparable to a Russian seminar. For example, when Gelfand, he did establish a seminar in Rutgers, and it did have a special spirit to it compared to the other seminars in Russia, but it was at 4 p.m. and everybody had to go at 6. None of this seminar that starts at 6 and ends at 11, and by the way, the Gelfand seminar would only end at 11 because the last buses were just about to leave, so people had to rush to get the buses home.
So it was a very social.
It was a very social place, a very warm place. It's sort of surprising because, of course, at these same kitchen tables where you would be discussing mathematics, you could not discuss politics because everybody assumed that there was some bug planted somewhere. And even though they also assumed that the KGB was so inefficient that they might not be able to understand what was on the bug, nevertheless, if you wanted to discuss politics, you'd go outside and walk in the park. There was a, you would never tell any Russian about the details of the life of another Russian because you never knew when somebody would get in, could get in trouble. And of course, people did get in trouble. People like Arnold and Manin could never leave during that time because they had made some political error. So the penalties were very strong for doing the wrong thing politically. But socially and mathematically, it was a paradise.
You said you often felt leaving it, that you were, leaving that kind of freedom and openness behind, or some kind of, you felt bad about leaving. It
was so sad. I was leaving my friends. These people were not able to visit me in the West. I knew I wouldn't see them again until the next time I came back to Moscow. Our assumption at that time was always that the Soviet Union would go on forever and these people would never be allowed out. Yes, it's the human relations. Well, I love the place too. But I assume that has to do with association. Red Square is honestly very beautiful. Strangely, Moscow didn't change its look when it became capitalist. It has a very characteristic look. There are these huge apartment blocks, and on the first floor is all these stores, and at the top is a huge sign. So when I lived there under communist rule, the sign at the top would say, "Glory to the Communist Party of the USSR," and the stores at the bottom would be bread stores, which might only have one sort of bread in them. Now the sign at the top says, "Drink Coca-Cola," and the stores have lots of things in them, but it really looks the same.
Still, Moscow University
Yes.
lords over the landscape there. It's this
Right.
huge monster of a building. So
Right. Is it beautiful or is it ugly? It's really a funny...
it's hard to say.
It's really hard to say.
Yeah, it's so outsized. It has to be judged on its own, I think.
Right. Well, of course, there are these 5 Stalinist buildings, and then also they were built other places. So if you think of it as representing Stalin, it's the most awful thing you could imagine. Yeah. And on the other hand, the mathematics that went on the 13th floor there was just amazing.
about how often and how long would you be visiting the Soviet Union compared to what you were doing here in the U.S. or in Paris?
Oh, during the time when I would visit, I would always go as an in-tourist tourist. So the most I could go was 2 weeks, and it was usually 1 week. I would sign up for an in-tourist tour. They would, that was the way I could officially apply for a visa without, getting somebody in trouble. I mean, if one of my Russian friends invited me, well, that wouldn't be so good for them. So it always happened the same way. Everybody else on the in-tourist tour would get their visa, and I wouldn't until a couple days before. And then at the last minute, I'd have it rushed to me, airmail, and the in-tourist people would say they'd never seen anything like this before. And then I'd arrive at the border, and everybody else would go through the border, and I would give them my passport, and the border guard would disappear, and these 4 or 5 very serious guys would show up, and they would go through everything I was carrying, look at every document, squeeze out the toothpaste, cut open the bread, and all that sort of stuff on the way in, and then they would do it again on the way out, every time. Sometimes with a strip search, not always with a strip search. They had a little room there.
So it took a lot of courage later on to bring all that money into the Soviet Union. You could have been searched at any time.
Yes, yes, right. When we finally were running the former Soviet Union aid fund for mathematicians, we discovered that there was practically no way to get the money into the country. There are lots of people who would do it if we gave them a quarter of the money, but of course this was in general money donated by individual American mathematicians. The idea of losing a quarter of it to Western Union, for example, for carrying it in seemed silly. So in the end I said, well, I'll just go and carry it, and it took I know the AMS was very wary about approving it. Right, so we had to declare the money on the way out, because it's actually illegal to take that much money out of the United States without declaring it, but not declare it on the way in, because it was well known that the border guards at the time had contacts. I mean, were likely to have contacts on the inside, and you would certainly get past the border, but the border guard would tell their contacts, here's a guy carrying this much cash, and this was enough money to get approximately 200 or 300 people murdered at the going rate. So we had to sort of hide it, and at the same time have it so that there was a plausible cover story in case the KGB agent found it on the way in. But we managed to make it on the way in without it. That time we were not searched. I guess it was the first time I had been in after the collapse of the former Soviet Union, and I guess they changed their protocol, so it turned out to be okay.
As time went on, so you were at Brown for several years, many
17
years.
Yes.
17 years. And then left Brown to MIT, and then MIT to the Institute. Can you say anything about what your thoughts were in making those changes?
I mean, all 3 places are totally remarkable places. Brown was the most pleasant place in America I've ever been. I mean, maybe another point I should make, one of the reasons I was unhappy at Harvard was, at least among the junior faculty and graduate students at the time I was there, it was a sort of a very competitive place. People were trying to get one up on other people. At Brown, we had some very good people there, and nobody was trying to do that. It was extremely cooperative. We had very wide-ranging seminars on all sorts of things. People from all sorts of different subjects would come. There was a remarkable collection of mathematicians at Brown while I was there, and we would all have seminars together. Joe Harris and Dick Gross and Bill Fulton and myself and Paul Baum and so on. When people ask me what my ideal place in America would be to be a mathematician, it would be at Brown at the time we were there. Of course, what happened was the whole group was lost at the same time. So I can't go back to Brown at the time we were there. Although Brown remains a wonderful place, and I think it's still true that it's a good place to do mathematics, sort of non-competitive environment. MIT is surely the most exciting place I've ever been. I still go once or twice a year, and when I go, I always make it a point to walk around in the corridors at midnight or 1 or 2 in the morning. It's just exciting at 1 in the morning. There's always life. People going around doing things, people in their laboratories working. Yes, in each case, I was always sad to leave, and I was certainly sad to leave MIT for a certain group of people. It's the ideal place. It's a place where being a nerd is the norm. Yeah, and the Institute for Advanced Study is a very, very unique environment. I don't know what to say about it, except that it's surprising to me that it was founded so long ago. It's been copied so often. Our director points out that something called Institute for Advanced Study with some decoration on the name, it opens more or less once a month these days. But nevertheless, it remains unique among all these institutions.
What attracted you about going to the Institute?
Well, I guess the freedom to sort of build whatever sort of group I wanted to without any constraints, and it certainly has the freedom and the resources. For example, when I got interested in materials, it was, the Institute hasn't had anyone doing materials there within anyone's memory, but everybody said, "Oh, great idea! Let's have a little group of people," and they were happy to support it with space and housing and financing as necessary. So it's if you want to try something new, you can just do it. It's really very nice that way. And also being near Princeton University and associated with Princeton University, you have the advantage of having graduate students, and if you want to teach, you teach. If you want to, I never have taught an undergraduate course while I've been there, but I'm sure everybody would be happy if I wanted to. I've taught a number of graduate courses.
And had a number of graduate students.
Yes.
Since then. So,
yes.
Yeah. They all seem to be doing something different. Every one of them. It's not like there's a McPherson school of graduate students.
Right. This has been hard on them. Even when I have several graduate students at once, the graduate students I have are all doing something different from each other. It's unlike, for example, Joe Harris has a algebraic geometry school at Harvard, which has been running for many years, and it's actually a beautiful thing. He'll have, a couple of Benjamin Pierce instructors maybe, and then some 4th or 5th year graduate students, and so on down to entering graduate students, and sort of everybody educates the next year, and you have this group of people sharing their knowledge and passing it back and forth. Whereas when I've had several graduate students, the norm has been I'll be talking to each of them, but they usually don't have enough mutual understanding that they can talk to each other, at least in a mathematically beneficial way, about their work. Of course, they've always been friendly with each other, and there's been the reinforcement of being able to have an affirming process of talking to somebody who's sympathetic. Sometimes we've had joint seminars, which will be everybody talking about their own specialty, but it's often each person talks about what they're interested in, and the other students sit there and politely listen because they want somebody else to politely listen when they talk. But so it has that negative aspect. But the positive aspect is I think mathematicians are very different from each other, and people have different talents, and the idea of graduate school is to pair people up with something that they're good at. And so if I had several people with identical talents, I would be happy to have them work on the same subject, but that hasn't happened.
Do they come to you with just, with an idea already of what their talent is, or do you have
No.
to help them find that?
You have to help them find it. It seems to me a miracle that it can happen at all. People, undergraduate students sort of have this myth as to what's going to happen, that they'll go to some professor and say, will you be my thesis advisor? They'll say, yes, here's a problem, and then if they don't get somewhere, they'll say, okay, well, here's a different problem, try this one instead. But that's, and that is perhaps how some people operate, but in my case, I say, well, why don't we do a reading course, so that the function of that is so that I can find out if we're compatible at all. There are a number of very fine mathematicians who I've refused to work with because I felt their strengths lay in some other direction, and by the way, I've always taken as my personal responsibility under those circumstances to find them a good advisor. And I'm very proud that some of these cases where I've played matchmaker have worked out spectacularly, and they've gone on to have a good career in that area. But I'm looking for whether we have any overlap at all, and if we do, what might be a good subject. So usually I have them do, sort of small projects where they do their own thinking rather than the typical thing, which is a reading course, learning the material necessary for the problem that I'm intending to assign them. And then later on, I try to arrange it so they discover their own thesis problem. And the art is to have it so that you have some backup. That is, you always look at what they're doing, and if in the event they don't find their own thing, you have some push and say, okay, so here's something. So you're always sort of shadowing them with some idea, but not telling them what the idea is, because it's much better if they find it on their own.
We first started really interacting over an issue that wasn't strictly speaking mathematics. You may remember that when the AMS had planned to have joint meetings in Colorado, in Denver, in fact, and they passed Amendment 2. Bus Jaco, who is the president of the AMS at the time, said, well, we won't meet in Colorado, and we moved to San Francisco. And for a lot of us who were gay, there was that was kind of a positive sign that people in the AMS would be receptive to there being a GLBT caucus, gay and lesbian, bisexual, transgender caucus. And I remember that some of us, and you were one of them, started a little email discussion group and organized the first meeting of that caucus in San Francisco that January. And I was wondering if you'd say a little bit about how you got involved and why you thought it was important.
Yes, well, I would say I was incredibly proud of the AMS when they made that decision. Reminds me a little when I was in my third year at Harvard, we had the big strike against Harvard's involvement with the Vietnam War, where as a result of this strike, ROTC was kicked off campus, and now it will come back. Now that that gays are allowed in the military, it will be allowed back on campus for the first time. But in any case, we had a strike, and I was the organizer for the Department of Mathematics, and we had over 90% of the young people in the math department were on strike, whereas the next department was like 50, and most of them were like 10 or 20. I mean, just the level at which people were willing to stand up for something they believed was much higher among mathematicians than the other groups at that time. I mean, it's still true that gays going into science and technology areas seems to be not so clear. when you read the gay press and people talk about what gays are going to do, I mean, you read about gay politicians and gay writers, gay artists of various sorts, gay movie actors especially. But the idea of a gay scientist, I don't know, I don't recall actually seeing any article about a gay scientist in the gay press. And on some of these online, it's actually much better in mathematics. I mean, frankly, I don't think there's any discrimination in mathematics. There was a time when a huge number of the people at MIT were gay, for example, the young people who were the only ones you would have known about. But in technology areas now, I'm a little bit more involved in applications. So I see. I mean, engineers are really upset. Before they accept a job at an engineering job, they want to hear all about, you know, is it going to be a problem that I'm gay at this engineering job? And many engineering schools, they'll find that they're the only out, if they are out, the only out gay person in the whole school. So I think it's still an issue, and I think it's very important that it should be discussed for that reason. Of course, the South is not the best place to grow up if you're gay. In fact, I guess there was recently a study that showed that the suicide rate among gay high school students is much higher in places like the South, which have anti-gay societal attitudes, than it is in places where the general ambient culture is more liberal on the issue. I must say, I wonder if it was easier for me growing up in Tennessee than it is for kids today, for some kids today, because when I was growing up, gays didn't exist. I didn't hear that there was such a thing as gays until I got into graduate school, actually. I realized that I was different somehow, and I regarded it as this problem that I had to solve, and that I would be like everybody else if I worked hard enough at it. And so I set in mind that I was not, well, whatever it was, I didn't have a word for it, whatever it was, I wasn't that, and that I would be straight. What there was a word for is people being effeminate, and that was the worst thing you could possibly be. And it didn't matter if you were gay or straight. If you walked in the wrong way, the guys would make fun of you and your life would be hell. And this didn't affect me so much. I was a nerd anyhow, so I didn't count. I was good at music and mathematics, and if you were good at those things, well, you weren't one of the popular crew, but you were sort of allowed to exist on the periphery of the school's cultural life. So in some sense, the only cost to me was the internal cost. I had this conflict, feeling that there was something terribly wrong with me that I couldn't discuss with anyone, because whatever it was, I recognized that it's something you wouldn't talk about even with your closest friends or your parents or your family or anyone. So that produced a lot of tension, increasing tension as time went on, but I didn't have to face discrimination. Actually, I have a funny story about this. Mark and I have lived together in many countries all over the world. We'll just rent a house, we'll be visiting some place, France, Sweden, I don't know, there must be 10 or 12 different countries, and we never had any trouble except in the Netherlands. There was a woman who had a house. I was at Utrecht for 3 months, Mark was there, and we halfway through, I mean, we had a wonderful house, but we had to leave it because the owners were coming back halfway through, so we had to find another one. There was a house for rent right in the center of town. It was definitely for rent through the university, and we went and looked, and the lady was very eager to show it to us until it was clear that Mark was going to be living there with me, and all of a sudden it wasn't for rent anymore. Now, I'm sure this was illegal, but what are you going to do? She said, well, I just discovered that, actually I don't need to rent this house anymore. And so I'm sure she rented it through some other auspices and didn't list with the university. And I remember Edward Loengha, who was very, very sensitive on this issue. So he went and did the legwork himself to find another house, and he, in his correspondence with the people we were going to rent from, he explained to them that you're going to rent to two very distinguished professors from the United States. Anyhow, I'm sure that the reason was that everybody in the Netherlands knows about gays, and she just immediately assumed that we were gay, and whatever biases, I don't know, she had, immediately applied to us, and she was, and she didn't want that. Whereas, as I say, we've never met that anywhere else. No matter who we rent from, they've never been unhappy with renting to two men.
Can I go back a little bit? I mean, you spoke about, not actually recognizing what it was, just realizing that you were different somehow, that
Right.
you were somehow not on the same wavelength. I think a lot of the gay mathematicians that I've talked to have expressed a lot of the same feelings, that there comes a time when you realize that you're not going in the path that everybody else is going. But it takes a long time to actually to identify what it is. Contrasted with what you often hear other people say, "Oh, I knew when I was 4," or something like that, or "My parents knew when I was 4." Do you have any thoughts on that? And
I don't know. It's a very interesting question how being gay and being a mathematician interact with each other. Just from my experience, I'm fairly certain that if you did a statistical survey, you discover that being gay is a positive factor to your becoming a mathematician, just like being Chinese is or being Jewish is. I mean, there are these cultures which have been very successful at producing mathematicians. Maybe it's because gay people are, in any case, marching to a different drummer, so they might as well do it in more ways than one. Mathematicians, when they are gay, tend to be not to be flamboyantly gay, shall we say. Maybe that has something to do with it, because my understanding is that people who are flamboyantly gay, it's sort of apparent to them immediately, that just because of their range of interest that they're different. So they never try to be not different. But actually, I don't know. The one thing I can say is I do remember that this group that we were just discussing, this internet group, had some discussion at some point about whether maybe gay mathematicians are more algebraists or more geometers, and the majority opinion was they're more algebraists. And I actually didn't contribute to that, but I thought, my God, what are they talking about? And I thought about you and me.
That's right, exactly. Closet geometers.
Right, exactly. Growing up in Tennessee, and where nobody mentioned the existence of gay people. So the first time I became seriously aware that there were gay people in the world was at the time of the Stonewall riots. In the next fall, the Harvard Crimson ran a wonderful series of articles about it. Was regarded as very avant-garde to discuss at the time. I mean, by that time I was aware that there were gay people in the world, but that's the first time that I ever saw anything that took it seriously. So Mark came to Northwest to Brown University as a graduate student in my second year there. And so in addition to being an extremely talented mathematician and to our working together, we obviously became very close friends, but in our own minds we were both straight. And this continued for a number of years until, I guess, there was the year, actually it was the year during which I met, I spent all the time with Gelfand when I was in Paris. I mean, we were separated for the first year in a number of years, and during that time, we both independently came to the conclusion that maybe we weren't as straight as we thought, and that maybe there was something more going on in our relationship than we had thought. So thought it was rather interesting that it happened when we were apart, and that it happened to both of us at the same time without our sort of communicating about it. But as I say, that era is probably gone, and I wonder what it will. I mean, there's no way that anyone could grow up in America now with that. I mean, just if you look at the front page of any major newspaper every day, it's just very, very clear that there are gay people, and that the pros and cons are debated all the time.
It's not so clear there are many gay people in the sciences and mathematics.
That's right. Although, as I say, in mathematics, I do know of a number of individual cases, but I have no idea how you would estimate how many there are, because I don't know what the probability if somebody's gay that I would know about it is. I don't know how to estimate that. It's interesting. I did love Tennessee. It's the South is incredibly beautiful, and for many years I would defend it against attacks by mathematicians from the North who felt there couldn't be any intelligent life south of the Mason-Dixon line. I'm sure you've met this as well. For example, the first time, of course, when I was there, the big issue was race. A number of the schools were closed while I was there, and when I moved there were 3 restrooms at the bus station, men, women, and colored, and then that disappeared during the time I was there. But the first time I met a real racist was when I came to college at Swarthmore. Some of the people, that was the time when there was busing going on, and people were really very, somebody who was willing to say racist things. I'm sure people were racist, but they were very genteel in the South. And they are, of course. Now I have to say, well, I guess I've had a number of experiences, so which I'm very sad about. When my mother died, the local paper ran a story about it, and at the end, as all such articles do, it listed the grieving family members. It listed my sister and her husband and me. And so I wrote a very polite letter saying, well, actually there's a 4th grieving family member, Mark, my partner, who should be considered as much a family member as my sister's husband. They printed it. And then later I went, and a very good friend of our family's, who was very nice and helpful, said he had seen my letter to the editor. He said he thought my opinion was very interesting. And it took me actually at least a month to process what he had been saying, because I hadn't been aware that I had given an opinion. I thought, how can anyone be more expert on who the grieving family members are than my mother's son? But apparently it was an opinion. So, well, anyhow, he's a wonderful guy, and he was very helpful to us, by the way. In a number of ways, we had a number of legal issues, and he continued being very friendly personally, but when I finally realized what it was he was saying with this, it appalled me. And, well, over the years, there have been a number of other such instances. For example, about 30 miles away from where I lived, the town council passed an ordinance that gays weren't welcome in the town. And then this received so much national attention that they repealed the ordinance the next meeting. But that happened. And right now, before the state legislature, as you probably know, there's a Don't Say Gay bill, which is, I guess, now passing the Senate. It probably won't become law this year, but probably will become law next year, who knows, where you're not allowed to even mention that there are gay people. So, for example, if you have a kid who's questioning his sexuality, you can't help him. Or, for example, if you have a kid whose parents are 2 men, you can't discuss it in class. that's apparently what's going to happen. So I must say that it's very sad for me.
Seems like an exercise in futility, though, in a way. I mean, like you say, in the front page of every paper, on every TV station, it's not like they can censor this, really.
Yes, well, there was a speaker last month at the American Philosophical Society. They decided to have a speaker on marriage, since there's this famous marriage happening in England, and since they have a playful attitude, they brought the national, or at least one of the few national experts on marriage, and somebody in the question session asked him about gay marriage, and he said, well, in his opinion, it's a done deal. And he said he couldn't think of any disadvantages to it. However, I have to say, while we're on this issue, Robert George, who's a graduate of Swarthmore College and who is a professor at Princeton University, is the brains behind the anti-gay forces. And as you know, they will run every referendum so far. You can rely on them in the last few days before the referendum to come up with some ad which has been carefully honed to the prejudices of the particular state, and they'll come up with it too late for the other side to answer. He's simply smarter than the people running the campaigns on our side are. I have to say, Swarthmore does produce smart people, and he's one of them. What can you say?
What can you say? Right. Certainly saw the evidence of that in Proposition 8 in California.
Right. They played their hand brilliantly.
You see yourself as kind of in the process of discovering yourself still in many ways. I mean, what would you say? What would you want to tell people about what the things that you have struggled with, and how that has played an important role in your life?
Well, without a question, the largest struggle I've had has been not with the gay issue or with the issue that I think differently from the mathematicians I talk to, but rather with the fact that I had and still have a strong stutter. So there are several ways you can confront this. Universally, psychologists recommend that you confront it by just talking through it and letting people suffer while it takes you 5 minutes. In my case, it would be 5 minutes. Usually it's only 10 seconds or so to say a word. At a certain moment, I decided, well, anyhow, I couldn't handle that. So I instead use another technique which psychologists recommend against, which is I avoid certain words. I can censor in a sentence I'm about to say. I can see where the risks lie and cancel it and say it in some other way. You get very good at this. Sometimes it means I start a sentence, stop it, and start a completely different way to say the same idea, and that's because I didn't see it coming and it's upon me, so I have to stop and go back. Well, as I say, people recommend against this, but this is what I've done. So this is, back when I was a student, the teachers would make me give oral reports, and people were very sympathetic, but anyhow, it was terribly embarrassing. As I say, it could actually take me 5 minutes. I would try to be saying a word. I remember trying to say one word in one of these oral reports in junior high school. It went on for minute after minute. I would completely exhaust my breath and then take a deep breath and start again and stammer it and completely exhaust, and then another deep breath. And finally the teacher said, "What is the word?" And I said it immediately. And everyone thought that was very funny, but that's how it is. Anyhow, it still affects my life. When I decided to become a mathematician, a big issue was, would I ever be able to be a college teacher? Well, fortunately, I have been able to be one, but there are some subjects I couldn't teach because some of the words you can't avoid and I can't say them. The AMS nominating committee pushed me very hard to run for president of the AMS. There's no way I could do that job. The AMS president has to announce people's names, award recipients, next speaker. If I can't say the person's name, that's one thing you cannot find a way around. I'm running a seminar with some guys at Rutgers and at Penn. We alternate universities, and the one rule I laid down is they do all the introducing, because I mean, I can introduce 5 people, but the 6th person I'm not going to be able to say their name, and that person's going to think that I'm somehow insulting to them because I refuse to introduce them. But there's just no way around it. So fortunately, the fields of mathematics which I deal in, there aren't concepts that have only one word associating to them that I can't say, but there are fields of mathematics with concepts that have only one word, and I just can't do it. I was actually very concerned about this situation because one of the things that makes it worse is talking on telephone. Another thing that makes it much, much worse is being recorded. So far, you probably haven't noticed that that I have a problem. But you talk about passing, it's much more, you know, if you're gay and people don't know you're gay, well, I mean, your gay personality only comes up every now and then. I mean, it's a minute-to-minute thing, not being able to say everything you want to say.
Although I would say you're displaying an incredible amount of verbal agility to be able to do this.
I have wondered if it has its upsides as well. I mean, you have to increase your vocabulary and learn to juggle things that other people don't have to juggle.
What advice would you give, or do you give your graduate students in starting out in a career in mathematics?
By the way, I've mentioned that I didn't have much in the way of mathematical conversations with my advisor. That does not to say that I am unhappy with my advisor. I think it was the best thing I possibly could have done to go to Harvard and work with Raoul Bott. If you look at his students, you find they're all over mathematics, and so am I. So somehow the spirit was transmitted. And I guess the same is true of my students. I don't know how they got it. I have never given a Polonius-style advice to my students, but they're also all over, and they also change on a dime. If some other new direction looks interesting, they're able to follow it. Just this week, there's this wonderful conference going on at the Institute for Advanced Study with the work of 2 of my former students being highlighted, and these are projects which I like to think they were primed to be able to take advantage of it when the mathematical culture had reached a certain point. But I have to say that there's one thing I strongly believe in, and that is somehow I got this notion in graduate school when I had no evidence for it, and that was that you should change fields every now and then, independent of anything else. I don't know where I read this, but David Hilbert actually did it. His average time spent in each field was about 5 years. Of course, he didn't revolutionize them all. Some of them he did, some of them he didn't. But I felt, when I read that about Hilbert, I felt it was a good thing to do, and I've tried to do it as well. It has its definite drawbacks. For example, my friends who have stayed in the same field, it's wonderfully rewarding. You go to you see the same people at Oberwolfach every year, and you become a grand old man in the field. All the young people know you, and they come to you with their questions, and you're able to answer because you're a complete expert in what it is that they're doing. It's a very satisfying life to spend your whole field, your whole career, for example, in algebraic geometry or in modular forms. But I decided not to do it. And at this time, already in graduate school, as I say, I had formed the idea that maybe the reason people have this myth that, or idea, in some cases it's not a myth, that mathematicians can only be active for a certain number of years, is because they try to be active in the same field. People should switch fields. Maybe their ideas will solve the problems in the next field even if they didn't in the last field. Of course, if you've been very successful, the odds are when you switch fields you'll be less successful, but that's okay. It's fun to be a beginner.
Would you say that's was one of the, not exactly secret, but one of the ingredients of Gelfand's success? That he,
Yes.
that he was everywhere.
Yes, I had formulated this already before I met Gelfand, but Gelfand was very proud of the following. What he says is fact. Every year, of course, he ran this seminar. Every year people would ask him, what is your seminar about? And he would tell them what it's about. They would say, that's not the right thing for it to be about, that's stupid. And he'd say, well, what's the right thing to be about? And they would tell him what his seminar was about 10 years ago. And he said the same thing was true when he discussed what he was working. I mean, he loved saying this. It was always with the same time lag, 10 years, that they would say, well, what are you working on? He would say, and they'd say, no, you should be working on this other thing. And it was always what he was working on 10 years ago. So he was quite pleased with it. His own self-image was that his expertise in mathematics was not the technical details, but rather the philosophy. He would think very abstractly, and sometimes it didn't work. I remember once he was very philosophically sure that something would work in our joint work, and it didn't. And he said simply, "I'm sorry, I have failed," which sort of overwhelmed me, but in any case. But it worked often enough. I mean, that's not quite my way. I feel you ought to at least know the language of the field you're going into and some of the technical results. I mean, you don't have to know them perhaps the same way other people do, but you have to have your own vision. My image has always been you pick on one or two examples that you can see in your own way and then interpret everything in terms of these one or two examples, and then you can learn a new field of mathematics that way.
Example and problem driven rather than theory building? I think many people wouldn't say that of you.
No, I'm saying that's how you learn a new field. I'm not saying, no, of course mathematics has the tension between the problems and the theory. I mean, what was wrong with these Dewdney problem books that people gave me in high school was that they were puzzles with no theory, no real reason to be interested in them as separate things. So let me tell you my view about, for example, Grothendieck, who's the world's most famous theory builder. So I worked in a number of things Grothendieck worked in, actually. My view of Grothendieck was he had this enormous formal intuition. It's like a review of toys. I mean, there's so many toys on the shelf. You're in this big toy store, you buy some of them, you know you're going to play with them for 5 minutes and then they're going to be boring. Others, you know you're going to, like the game of chess, you're never going to exhaust it. You're going to play with it and it's going to just get better and better. But you, in the toy store, don't know, okay, how to tell. If Grothendieck considered it, it's going to be one of the ones you can keep playing with. So it's not that it's a big theory, it's that he somehow his... I'm talking about from the personal rewards point of view, but whenever I was playing with a Grothendieck toy, it was just so much more fun. But yeah, for me it was a toy. I mean, I was playing with the examples. Here you have something that works in all these examples. Maybe you can make it a proof. Sometimes I found things Grothendieck didn't know, fine. But it was always by playing with toys, not by some formal intuition, which I feel Grothendieck has, and not many people do.
Your own personal working habits, so you tend to work late at night, early in the morning, or?
Well, I'm cursed with a 26-hour day. I measured it The first time I could was when I was at MIT. They have this IAP. They take every January off, and all these neat things happen. The whole energy of MIT comes forward, people doing all sorts of things all over the Institute. So I figured, okay, there are no classes. I can find out how long is my day. So I went to bed when I felt like it, got up when I felt like it, and I discovered my day's 26 or 27 hours. So as a corollary of that, or not a corollary, but I understand it's often in the same people, my moments of greatest clarity are late at night, and my moments of least clarity are in the morning. So that makes it rather hard, because then you have this insight, you want to pursue it, you'll pursue it, but then you have to get up in the morning, and then you don't have much sleep. Anyhow, it's not too good for building a life, but anyhow, that's how it is. But it is nice in terms of the schedule of organizations, because that means that I'm at Brown or MIT or the Institute for Advanced Study after midnight, and that's very peaceful in the sense that there aren't people around, there aren't secretaries who are saying you have to read this and approve this, sign this. You can just focus. I should say my colleague Jean Bourgain works as late as I do, so we often see each other at 3 in the morning. At MIT, there were always some people who worked that late as well.
Which touches on something interesting that you said, that often people think that you get the impression from other people that they think you think very algebraically.
Well, of course, so as I mentioned, I strongly believe in the unity of mathematics, and I have spent my time working in many different mathematical areas. In general, these have been things like modular forms, algebraic geometry, even number theory, combinatorics. These have been things where people's thought processes are usually logical or algebraic rather than geometric. So what I've often, one of the great reasons why you should regard mathematics as a unified whole is maybe you can bring ideas from something else. So, it's actually turning around. It's incredible to my mind that the people in modular forms have no conception of what a stratified space looks like, and yet that's what they're dealing with all the time. That's exactly these compactifications of modular varieties are all stratified spaces.
I think you had said at one point that you do think very geometrically,
Yes.
and very almost physically sometimes, and
Right.
which is not at all aligned with the kind of formal algebraic image that people have of some complex theory like intersection homology.
That's right, and you'll discover that many of my papers are written with a very algebraic language, because you're trying to communicate with people with an algebraic bent. Yes, it becomes hard, because I'll be talking to somebody. They'll know what papers I've written, so they'll assume that I'm an algebraic geometer, and they'll start using certain language, and I'll find that very difficult. Until I translate it into my own language, I can't really even understand it. But to them, they're talking, their words equals the subject. To me, their words is some pale imitation of the images that I have. So I've often found myself trying to pretend I'm something I'm not, in that sense. That is, in order just to have an ordinary correspondence, an ordinary discussion with some people in algebraic geometry, I'll find myself, quickly translating things into their language and translating their things back.
Passing,
yes. I've often felt like I'm not really a mathematician, like I'm this fake who just happens to have some geometric insight and is pretending to be a mathematician, and I've been very successful at it. I guess there's another question one could answer about the future of mathematics, and that is general trends like, will it become more abstract? Will it become more concrete? Will it become more example-oriented? And I actually gave a canned lecture, which I delivered several times about this, once in a millennial conference in Jerusalem, where I took a number of these questions and plotted my best guess over time. And I discovered they're all cyclic. For example, one of them was the concrete versus abstract. So you think about it. I mean, in the early 20th century, everything was very concrete. And then mid-century, Bourbaki came along and everything was extremely abstract. And later in the century, concrete became popular again. I remember having a slide on which I had written John Conway as one of the names under the more concrete becoming popular, and Conway happened to be in the audience of the talk. But in any case, I plotted a number of such things and discovered that they're just cycles with approximately a 50-year time span. So my prediction is that those things will continue to cycle, and that the period will stay approximately the same, and that it's good for mathematics that it cycles, because it gets away, you sort of sweep out the old and usher in the new. I mean, gee, the concreteness that came in after Bourbaki was so much more effective because Bourbaki had laid some foundations. So the whole cycle is very important, I think.
So can you say something about where your work is going now, where you think this area of mathematics should be developed, and how?
Formally on material science, but what I'm really doing is the topology of very complex spaces. So let me say a little bit of background. Just as I believed and still believe that any argument that manifolds are important is really an argument that singular space is important, one of the things that topology should consider is extremely complex spaces, like the Sierpinski sponge or something like that. And I feel this hasn't been adequately developed. Now, I've actually had in mind to do this for some time. I feel you should change subjects every now and then. I always felt that I'd like to make a rather larger change near the end of my career. I had two in mind. One was dropping mathematics completely and becoming a composer. Actually, I don't think I can morally do that and stay a professor at the Institute for Advanced Study. But in any case, I chose the other one, which was to become interested in applications. So let me say what complex spaces have to do with applications. First of all, in terms of singular spaces, the whole key was finding the right class. The early people who were looking at made-up singular spaces, they didn't get anywhere. They didn't produce good mathematics. So I felt you needed to find the right class of complicated spaces. Now, many complicated spaces have been known for years, like the Sierpinski sponge, for example. That dates back from the earliest days of point set topology. And while it does have a nice universal property, it's and maybe things like it do appear in a few applications, a few instances. At least it's not, in my view, the most important thing. So I looked around, where do very complicated spaces actually arise? Well, they arise in materials, and in particular, I'm interested in what they call the mesoscale. As near as I can tell, materials scientists use meso for something that's very small compared to us, but very large compared to atoms. So you're looking at things on the order of microns. There are many amazing structures in materials on this scale that are basically topological in nature. So my idea was to actually start with these and try to find things of interest to actual engineers who are dealing in materials. Let me give a couple of examples. I mean, look at the steel beams that held up the World Trade Center, for example. Well, these are not solid pieces of steel. These are very complicated things. So in the first place, they have lots of little grains, little crystals of steel oriented at various orientations. This put together is a cell complex, three-dimensional cell complex, which of course Poincaré introduced cell complexes in his very earliest papers of topology. But Poincaré's idea, actually he introduced them, as I understand the history, it was in response to criticisms of Max Dane, where Dane was saying, look, your theorems aren't quite right, and so he wanted a more rigorous development of homology theory. So his idea was you make it a cell complex and then do something to the cell complex, and then the cells drop away. But many of us love cell complexes. Now, in material science, the cell complex is the interesting thing. The global homology of this beam is usually pretty trivial. That's not the interesting thing. It's actually the cell complex structure. Or another thing that the beam has is lots of little line singularities. These singularities are, in my view, I'm going to develop this in a summer school I'm going to give this summer. These are homology classes with coefficients in a very interesting local system. But what's interesting about them is there are very, very many of them. Usually you think of homology, you think of there's a whole, and your interesting homology class is one cycle which captures the whole. In this case, you'll have maybe Avogadro's number of these things all lined up, and you want to think about that in some interesting way. So in my view, you have to think differently. I mean, the spaces that come up on the meso scale, their Betti numbers tend to be 10 to the 23rd. Nobody cares that the Betti number is order of 10 to the 23rd. You have to have a new question, just like for the study of singular spaces, you also needed to find new questions. So anyhow, I'm a believer that this is something that has to come, but in order to get there, you need to look at the naturally occurring things. So what I actually did is I walked into a series of material science courses. I was actually quite a popular figure among the material science graduate students at Princeton University for a while. I was the old guy who sort of came in and sat in the back row. And in the end, I ended up writing a paper with David Svrlovich, who taught the first of these courses that I took. We solved an old problem that turned out to be very famous. I think this more or less illustrates a point that I keep making of the unity of mathematics. I think the first serious geometer who learned about the problem would have solved it, but it happened to be me. So von Neumann, you have all these grains, or I mean, actually, von Neumann was considering foams. So let's talk about a foam. Foams are fascinating things, absolutely fascinating things. You can have two-dimensional foams. You have a couple of glass plates very close together, and then you have a foam. In fact, the way people do research on it now is they put the glass plates very close together, and they put it on a Xerox machine, and that records the foam, and then they let it evolve for a while, and then do it again, and you get another picture, and then you can compare the two pictures. So von Neumann discovered this beautiful formula for the rate of growth of an individual bubble in a two-dimensional foam. And this was in 1952, and then Mullins extended it to this grain problem I was discussing in 1956, but you can find in many material science textbooks as an open question, what's the three-dimensional analog to this? And there's a huge literature. Well, it turns out there is a precise three-dimensional analog. And as I say, I think it was sitting there waiting for the first geometer who understood the question, but anyhow, I did. And it became, it was a sort of a wild ride because it became a big news item. Mathematicians at the Institute for Advanced study beer foam. This was like a headline-producing thing, and I was getting phone calls from newspapers all over the world for a while, and I just stopped answering. Well, I don't answer my phone anyhow, but I stopped answering emails. And, we were getting well over 50,000 Google hits on this news item. I mean, that's kind of funny. So it's interesting sort of starting a question like that, but that doesn't still address my real issues. So we have a little group, and we're studying it, and I'm very enthusiastic, but I mean, we're clearly not going to do the whole thing. When Poincaré, well, when he wrote the paper which launched homology in this analysis situs paper in 1895. Well, I say that, of course, everybody knows there were precursors, Euler, Mobius, and so on, but and Betty, and in fact, Riemann understood an awful lot, but he didn't communicate it except by talking to Betty. I mean, there's a whole history before Poincaré, but anyhow, when he launched the first thing, his introduction to the paper is really worth reading. He apologizes for being so wordy in the paper. He takes all of 100 pages to found what, I mean, surely, at least in my view, if there's one concept which summarizes 20th century mathematics, it's homology theory. I mean, it's permeated almost everything. So here he's introducing that in 1895, and he apologizes for taking a whole 100 pages introducing it. He says he prefers to be taken as a little bit gossipy than rather than to be taken as unclear. So among other things, he says, why am I spending all of your time, all of your 100 pages, in talking about this new subject? And he says, well, the reason is everywhere I turn, it comes up in applications. And he gives a few. He talks about a group application he had in mind, and he talks about a dynamical systems application he had in mind. As I say, in my view, these all are really arguments for singular spaces. He does not talk about complicated spaces at that time. At that time, I don't think, Cantor was pretty recent. I don't know, I don't think people were so much aware of the existence of, I mean, in fact, you have to say Mandelbrot had a huge influence on mathematics until he came along. People weren't interested in complicated spaces. Let me digress from a digression to tell an anecdote about that. My first course in materials science was at MIT. There was this old man, I've forgotten his name, old materials scientist, and he said he had shattered a piece of steel, and then he looked at it. It was rough. He looked at it under a microscope. It looked the same. He looked at it under a higher powered microscope. It still looked the same. He said, what's going on here? This must be interesting mathematically. He went to the math department, which was already a superb math department. It contained Norbert Wiener, for example. He asked around, have any of you ever heard of such a thing? And the answer was, A, we've never heard of it, B, it's not interesting. So anyhow, talk about a missed opportunity. Well, it is interesting, of course. And Mandelbrot made that clear. On the other hand, the people who do it tend to be analysts and measure theorists at the moment. And people who study turbulence would never go anywhere without complicated spaces. But other mathematicians, topologists, they don't care. I mean, what is a Betty number? A Betty number is a finite thing. It's a small number. I don't know how big it is, but it's no more than 100. I mean, whatever. Or you have a formula for it, and the interesting thing is the formula. Or maybe you care whether it's odd or even. Certainly, if the Betty number is Avogadro's number, whether it's odd or even doesn't...
You throw up your hands.
Yeah, right, you don't care. That's certainly not the important thing about it. So I think the important questions just haven't been elucidated, and that's what I'm hoping to do. We haven't done it yet, but we have our little group, which, as I say, my colleagues at the Institute have been very helpful in allowing us to constitute a little group, and now we have larger simulations of these 2- and 3-dimensional grain structures I was talking about than anyone else does, and we're measuring things about them. Some things are interesting to measure, others aren't. We're having lots of fun. Right. So the Institute for Advanced Study has some magic to it that it has stayed on without too much change in format for its entire period of existence. And it's a very interesting question to me why it's been so stable. But I don't have the answer. I mean, of course, the financial answer is that the Bambergers sold Bamberger's department store a few weeks before the crash rather than a few weeks after, so they had enough money to give it an initial endowment. But it's received very generous gifts since then. But what I can say is that people, very remarkable people, have been associated with it, and everyone loves it. Everyone takes it very seriously, and it's not at all obvious that this should happen. You have people as diverse as Pierre Deligny or Enrico Bombieri or Robert Langlands, who are very completely different people in terms of their personalities and their beliefs. But when it comes to the survival of the Institute for Advanced Study, they're willing to do anything for it. And my understanding is that the same was true for the people of earlier eras, like André Weil, who got in these enormous fights with the director of the Institute. Well, that wasn't because he was trying to destroy something. That was because he valued something. He thought the Institute was this wonderful gem. I know this because I talked to Armand Borel before he died extensively about it. He thought the Institute was this wonderful thing and it should be preserved, and the director was trying to take it in the wrong direction, and he wanted to try to correct that. So every time there has been a serious dispute, and it happens, both sides of the dispute have wanted what's best for the institution. So now, for example, well, I mean, this is a trivial example, but I'm sacrificing a large part of my summer to be on the director search committee at the Institute for Advanced Study. Well, it's very, very important that we get a good director. I have other things I really want to do with my time, but I'm willing to do this. And the same is true whenever anything needs to be done. For example, we don't, in the School of Math, we don't really partition the work. We don't make deals like, okay, I'll do this if you do that, so much as everybody believes everything has to be done. So we say, who's the right person to do it? And if one of us believes someone else is the right person, then that person should do it. I guess it's happened more often than I expected when I came, that my colleagues believed that I was the right person to do something or other. Anyhow. So I don't know why it inspires so much devotion, but I do think some total purity of purpose. I mean, it's not trying to make money. It's not trying to develop a new drug. It's not trying to. I mean, people ask, is my work in material science, is that going to make better structural steel? It might, but that's not the point. I'm doing it for the reasons I said, because I think it's going to be good for mathematics, not because I think it's going to be good for building buildings in Manhattan. So I don't know, this may just move the question to another thing. Why do people become so devoted? But they do. I mean, Jim Simons, for example, the people on the board, Charles Simoni, our current director of the board, they're all, I mean, it's not like other boards. They really care about the place.
I think they recognize what an incredible prize they have in the faculty there. And that's it's really remarkable. It's been that way since the beginning. And you know, certainly for all of us, the legends walk the earth there, you know.
Right. Well, hope we can maintain that.